Today we're going to be covering convolutions in MATLAB. There's going to be two parts. Part one is doing this problem. Given two functions, the f of t impulse response, so a system's impulse response, and then the g of t system input, how do we get this output system response? Then in part two, we're going to transition to look at smoothing functions. Given some raw random data in the top left, let's apply two different smoothing curves to get this convoluted smooth data. Let's say you have these two functions, for example, and your professor asks you to take the convolution of them in MATLAB. It's a very straightforward problem, but there's a couple of things you need to pay attention to in order to get the correct output response. I have a couple things defined here to make this a bit straightforward. Briefly, I'm just clearing everything to start, defining a dt, which we'll use to define our time variables for both curves. Here I've got the f of t defined. Here's our t values going from 0 to 2. And then f of t is just going to be 2 minus t1. That's according to this equation on the left, 2 minus t here. And then for curve 2, we're doing a similar method, but we need to go from negative 2 to 2, as I have here. And then the g of t function, I've just created it as 3 times a vector of 1s. 1s creates that vector, and then we're doing it in a matrix a 1 by the length of t. So however many values this is, we get a 1 by that many values here, times 3, which should just give us values of 3 going from negative 2 to 2. Then the convolution. This is the simple way to do it, and this is likely what you'll try first. Conv of ft g of t, which are these two functions we've defined here. We'll call that the y of t out as the response. And then I have a whole bunch of commands just to plot everything. If you're confused on any of these commands, I have a whole separate video on doing plots where all of these commands will be used. Check for the description for the link to that video. Let's go ahead and run this and take a look at our output. All right, the impulse response is looking good, going from 2 all the way down to 0 at t equals 2. The system input seems to match as well. We're just values of 3 straight across, and those both match what we're looking at in our problem statement. However, our f of t times g of t, the convolution for the system response, should give you a couple warning signs here. The shape looks good, but what's happening to the amplitude? We're going all the way up to, what, 63-ish here? That seems a bit high. And our t, that doesn't, you're right, something's not looking right here. The problem that we're actually seeing here is that everything in MATLAB is still very discrete. We like to think of these curves as continuous because that's what they look like. But in reality, all these variables, t2, g2, t1, ft, these are all extremely discrete. And when we're doing the convolution, we're doing the discrete calculations every dt times. It's kind of hard to understand, so let me just show you the graph then if we did 0.01 for our dt. Now our y for our response is in the 600s, and our time goes out to 600. Let's try 0.001 here, and we'll see again, this response is just scaling up by our dt. That means that we need to take out this factor, and to do that, we're going to multiply the outputted convolution by dt. If we do that and graph it, we'll see, boom, look at our y values. That looks perfect, goes exactly up to 6, which is what we'd expect for an impulse response of 2 and the input at 3 consistently. It should build up to a maximum value of the f of t max times the g of t max, which is 6 here. However, our t scale here on the x-axis is still way off. That's because what we're currently plotting is just right here. We're plotting yt. The output of a convolution will only give you the y values. It only gives you these vertical y values going from 0 to 6. It doesn't create the time scale for you on the x-axis. So we need to create that. To do so, I'm going to define a ytx variable, which will be used right in here to plot our ytx versus the yt values, which are the y values that we get from this convolution. And we know that we're going to use dt again to scale. So let's think about this. We want to do all the values in yt. So let's do 1 through the length of yt here. And I'll show you what this looks like in the command window. So that gives us all these indices, basically. The indices going from 1 all the way to 6001. That's how many values we have in yt. If we multiply that times dt, it should scale it just a little bit here. Actually, a lot of it. This is a vector, so we need to use vector multiplication, dot star times dt. Let's plot this, and now look at our x-axis here. Now t is going from 0 to 6, which makes a heck of a lot more sense. Last thing we need to do is shift this timescale to align with our g of t system input and impulse response, okay? We need to shift it so that the first time that we're getting a value of the input, so we start inputting values all the way at -2 to the system. So we should start to see this rise happening at -2. To do this, we're just going to add this first value to our x values of the system response. We do that right here. Plus, I'm going to call out, here's the system input. We want the first value of this t2. So I'm going to call t2 first value, which will be -2, and that'll shift all of these values by -2. We graph this, and perfect. Now we have -2 starting on our x-axis, going all the way to t equals 4 when we finish here. Focus on your knowledge of what the output should be of this convolution, and then work backwards to make MATLAB do what you want to do. We're back to part 2. We're going to take a look. Firstly, we're going to create some raw data, like we see here in the top left, and this is actually completely random. I've developed 2 smoothing curve functions, a rectangular curve, which is just one straight value, and then the Hamming smoothed curve here. And then lastly, we're going to do the convolution of the raw data and the smoothing curves, and we'll see these 2 outputs. The rectangular curve having a lot more kind of jitter in the solution here. It's not super smooth, but it still is a form of curve smoothing. And then the Hamming curve, which is more of a kind of upside down cosine here, depending on what phase you're looking at, it gives us this really nice red smoothed curve. And we'll look at how to implement both of these. Here is the code. Now a lot of this I'm not going to go over because this is other MATLAB concepts, but I'll give you a brief run through. We're generating some random data, and I'm just plotting it here. Then I'm creating these smooth curves. The amplitude of the curves is up to you. I'm just doing 1/61 because it's left over from our previous problem, but I'm using this ones function to generate some ones, and then I'm defining that second curve, that cosine looking function, right here. It's a bit complicated because of the phases and getting things to fit into one cycle and so forth, but that's there. Plotting that all here. Here's the actual text for the convolutions. I'm taking that raw data, that random data, and convoluting it with the different curves that I created. Now when we plot this, we're going to see that we actually have a bit of a trail off at the end. See how our raw data only has 1,000 data points, but yet our convolution ends up with a few more here at the end, about 1,060. In fact, it's probably 1,061 because we have 61 values in our smoothing curves. To get rid of that, to truncate these last 61 values, we need to add the argument same here. And that makes the output, rec smooth, have the same number of values as the first argument, which we have as data. Let's plot this again. And now we'll see Here we end with 1,000 values, which is more accurate when we're working with a raw data set of discrete data values. One notable difference with this method is because we're starting with raw data and not using functions like we did in the part 1 of this video, we don't have to worry about the whole dt shifting, you know how we did dt times, all that stuff. We don't have to do this, and you might be asking why. It's because we started with raw data and we didn't have to create that first function from scratch. So we don't have any dt's to worry about. The convolution simply gives us the answer that we're looking for. Thanks for watching. Hope you enjoyed. It's a very cool thing to do, using these convolutions to smooth curves, get answers, and see how systems respond. Thanks for watching. Have a great day.